Then, Barrett, if you are ready, could you please start your talk?
Yeah, this is just, I'm Jeremy, just for Jeremy, not there.
Just live the life, bro.
Oh, sorry. I'm sorry, my mistake. He is Jeremy Marlon, and from independent researcher. Sorry.
Okay, thank you.
So quick.
Hi everyone, my name is Jeremy Morgan. Today I'm going to be presenting our work IKFlow, Generating Diverse Inverse Kinematic Solutions. This work was done with my collaborators Barrett Ames and George Konadaris. We're presenting a new IK solver, IKFlow, which generates IKFlow solutions in orders of magnitude time faster than current state-of-the-art methods. So a quick recap on inverse kinematics. I'm sure we're all pretty familiar, but tasks are often described in the workspace, but we can only control the robot in joint space, so we need a mapping from test space to workspace to accomplish tasks. So for a concrete example, we have this welding robot. It needs to follow some path in test space, so we need to find joint space configurations that lead the robot along this test space path. So importantly, for 6 DOF robots, there's going to be a finite number of solutions, but for 7 DOF or higher redundant robots, there's going to be potentially an infinite number of solutions. So existing solutions fall into 2 categories: those that analytically solve the problem, and those that use nonlinear optimization. So analytical solvers work by beforehand analyzing robots' geometry in order to find analytical expressions that can be plugged in to solve. And this is really quick, like you can calculate within microseconds. But there's some limitations, like you need to define a redundancy parameter, and parts of the solution space may be unavailable. In contrast, we have nonlinear optimization methods. These work by doing an optimization procedure on a randomly drawn initial joint configuration and iteratively move end effector closer to the target pose. So the benefits are they work out of the box and can get arbitrarily accurate solutions, but they will only return a single solution if one is found. And they may fail to find a solution even if one exists. So as opposed to these existing methods, we present IKFlow. It calculates IK solutions in parallel on the GPU, which enables users to sample thousands of solutions in just milliseconds. Thus, IKFlow falls into a new category of IK solvers in which an approximation of the entire IK solution set is returned when queried. So in the scene on the right, we see the Baxter robot. It's tasked with picking up this mug, but the kettle's in the way. So what we can do is run IKFlow, get a bunch of solutions, and then evaluate which ones are valid. So without IKFlow, the robot system would need to repeatedly call an IK solver until either valid solution is found or the program just gives up. But with IKFlow, we can get a bunch and then evaluate them according to some application-specific criteria. So under the hood, IKFlow treats a set of IK solutions as a distribution and uses a conditional normalizing flow network to fit this distribution. The normalizing flow network can then be sampled from when solutions are desired. So when sampling from the network, noise from a latent space is sampled from a Gaussian distribution and passed through each coupling layer in the network. The initial latent noise is transformed until it is eventually treated as an IK solution. In this video, we demonstrate this mapping. So on the 2 plots on the left, we see the first 4 values of a latent vector. For this particular model, there's 15 values in total. And as we vary the latent vector, we can see how that changes the IK solution. So we'll look at the quantitative results next. So we trained 10 different kinematic chains for 6 different robots to validate our method. When testing a model, we measure the average positional and rotational error of the end effector when the robot's configuration is set to the IK solutions generated by IKFlow. The positional errors of all the final trained models are within 1 centimeter, which is low enough error for many applications. And they can be easily refined using traditional IK solvers. And we're also working on our own parallelized IK solution solver that's provided with the IKFlow software. So we'll look at some qualitative results now. We have 3 robots. For each of these robots, we have 25 IKFlow generated solutions calculated at every time step, which are tracking a mug's trajectory. So in these motions, the same latent noise is used in each of the IK solves. And because of this, there's smooth motion for each of the solutions. One way to think about this is that each of these 25 solutions is tracing a potential motion plan for the robot to follow across the trajectory. We can see that they're all highly accurate with a couple erroneous solutions. So we'll now look at runtime. In the figure on the right, we see runtime as a function of the number of requested solutions. For IKFlow, track IK, which many of us are familiar with, but it's a common nonlinear optimization-based solver used in practice, and track IK seeded with IKFlow. We can see that track IK generates a single solution faster than IKFlow, but for 6 solutions or more, it becomes faster to run IKFlow, or run IKFlow and then track IK. We can see that the blue line appears nearly flat in this plot. That's because we're calculating on the GPU in parallel, as opposed to a sequential solving that track IK is doing. So the runtime depends on the architecture of the underlying conditional normalizing flow model. So we can get faster runtime if we use smaller models. For all of our final train models, we can get 100 solutions in under 10 milliseconds. Yeah, so thanks for attending this presentation. Please check out our project page where you can find instructions on how to run IKFlow for yourself. Keep an eye out for our IROS and move-it packages, which are under development. Lastly, I just want to say I would love to see this getting used in the community, so if you have any interest in using this yourself, please let me know. I'd be happy to help integrate it with your system, and I'd be happy also to train an IKFlow model for your particular robot so you can use it yourself. So, great, thanks. Happy for any questions.
Yes, please.
So, is this based on the ROS or ROS 2?
Sorry?
ROS or ROS 2?
Neither. It's just a PyTorch
So you
implementation.
mentioned that there's a ROS package?
Oh, I'm working on that right now.
Okay.
So I'm planning on releasing a ROS package for different common
Okay, is it
robot
going to
models.
be ROS based or ROS 2 based? Not sure.
Not sure.
Okay.
Maybe both.
How did you generate the data set for your normalizing flows, to train your normalizing flow? Because that should also have this multimodal solutions. Right?
Yeah.
Yeah, so how did you get those data sets?
Yeah, fortunately that's pretty easy for us to do. We just randomly plug in like configuration space configs and then do forward kinematics to find the realized pose, and then just do that a bunch of times and we have a data set.
Okay, so you ran forward kinematics and then flipped it to act as an inverse kinematics kind of like that?
Yeah. So we can just get like millions of configuration and end effector pose pairs just by plugging in random configs to the robot.
Oh, thank you for your great presentation. And I also have time with the normalizing flow for robot motions. And I found that in real robot, the training normalizing flows the loss of it can be diverse and fair to train because of the numerical problem. Have you tried for real robot or any other case? In another case, can you find this problem and solution?
So you're asking about like training instabilities of the normalizing flow?
Yeah, because as you know, normalizing flow use relative low light hood as a loss, and then it means that if we found outlier during the training data, and then relative low light hood become infinity, so it's easily fair to train in real robots. So
Yeah.
How do you deal with it?
The training process is actually quite stable. There's only a single loss term, and we found that, you know, unless your learning rate is like obviously too high, that it's trying to stabulate. So that's actually wasn't a problem for us.
Okay, thank you very
Yeah,
much.
thank you.
Yes, please.
Hiya. This is really great. Your work generates many configurations very quickly, but if you're working in a really confined or busy environment, you'll have many of those will be in collision. Does it take a long time to check every single one? How many do you return? Is there some way to limit it so it's quicker?
Yeah, so like for collision checking, you're asking about? Yeah, so that's kind of outside the scope of like this particular paper, but it's something that we'll look at in future work, and maybe with GPU-based occupancy map, that could be some kind of collaboration.
And can you limit the number that you return so that that's
Yeah, that's just usually just however many you want. You just define your batch size and then run that.
okay?
Yeah, thank you.
Thank you. Okay, let's start the speaker.